So we start with this new topic today, the permutations. So we define the permutation. First of all, someone who was coming some noise, I think we should kick them out so that they learn a lesson. You need to keep your microphones off. I think he has gone quiet now. Fine, we can continue. So we continue. We define a permutation. Permutation is simply as over a set of n distinct objects is simply an ordered arrangement of these objects. We'll be looking at some examples shortly. So what we are defining is a permutation. Is a set of n distinct objects. Over a set of n distinct objects, it should be objects, I think, not object, is an ordered arrangement of these objects. So that is one. So for instance, if I have three objects, A, B, C, that is one of the possible arrangements of the objects, and I call this a permutation. I could also order them with A first, followed by C, and then I put B last. That's another arrangement. So these are all examples of permutation. So when we talk about permutation, we are looking for all arrangements of these three, ordered arrangements. The keyword here is ordered. So they contain the same elements, but the order is different. So each order is a different permutation. So the second thing we look at is an R permutation of a set of n distinct objects, is again an ordered arrangement of R distinct elements of the set. So here we have a set with three elements. So we can, for example, do a two permutation from this set. It will be just an arrangement, an ordered arrangement of two elements from that set. So this is a two permutation, and it's different from BA because order is important. So this is really important, the order for permutations. So these are two different permutations, and they are two permutations because we picked two elements out of a set of three, and there are many more. So you can have AC, that's a permutation. You can have CA, it's another permutation, and so on. What else can we have? We have BC, we have CB, and so on. So let's look at some example. So suppose we have this set. This set has three elements. We can arrange them in this form with three as the first, one as the second, and two as the third. And this gives us a permutation of the set S. And this gives us all the other permutations. This gives us all the other arrangements that we can get, ordered arrangements in particular. So 1, 3, 2, 2, 3, 1, 2, 1, 3, and 3, 2, 1. If you count all of them, you end up with 6 arrangements. The first one is 1, 2, 3. Second one is this 3, 1, 2, and then the remaining 4 are here. So you have a total of 6 different permutations of the set S. Right? Did I set up the recording? Oh yeah,
yes,
it's running.
indeed.
Yes.
Okay.
Yes.
So now here is an example. Again, we have a set with 3 elements. and we want to look for two permutations. An example of a two permutation is this arrangement where one is a first and two is a second. But we have 6 other two permutations where we arrange 2 elements at a time. So because order is important, this arrangement 1, 3 is different from 3, 1. Also 2, 3 is different from 3, 2. We consider order, and then we can see we have a total of 6 two permutations of the set S. So there is some notation we shall introduce now. The number of R permutations of a set of n distinct objects will be denoted by this P and R. Some books will write it as in this form where you have P and then R. It will mean the same thing. So some books will write it as this, but the book we are using is using this notation. So we shall stick to this notation of P and R. Someone who is not muting the mic, I think I will kick them out. We need some discipline in the class. He has gone quiet. So there we are. We have, so here is an exercise for you. You have a set of 4 elements and you need to determine the 3 permutations and also the 2 permutations of this set. So the 3 permutations, I can write some examples, but you will complete this in your own time. So if you are looking for the 3 permutations, I'll just stop there as a shorthand. So the 3 permutations will be subsets, but ordered as like 1, 2, 3. That's an example of a 3 permutation of this set. You have 1, 3, 4, and so on. So you need to be able to list all these. That gives you the 3 permutations. You also will need to find the 2 permutations. And now what you will realize is that 1, 2, 3 and 1, 3, 2 are different, right? And a rearrangement of these same elements is different, 2, 1, 3. They all have the same numbers in them, but they're different arrangements. So each of them is different. But you have 2 permutations. That means you pick 2 at a time and arrange them. So you have 1, 2. The other arrangement that is ordered is 2, 1, and so on. So you need to find all these 2 permutations and all of these, the 3 permutations. You should do that as an exercise in your own time. So here is a theorem which shows us how to count the number of R permutations of a set with n distinct elements. And the claim is the following, that this number, the number of permutations, number of R permutations, not just permutation. There's still someone who is, you guys have no discipline at all. Okay, so we are making this statement. Anytime you want to compute the number of R permutations of a set with n distinct elements, that's the formula we should use. So for instance, in the previous example, we were looking for the number of 3 permutations, the exercise, not the example. Number of 3 permutations from a set with 4 distinct objects. So this tells us that the total number should be 4 multiplied by 4 minus 1 multiplied by, is it 4 minus 2? That should be the last one, right? So what will this be equal to? This will be 4 multiplied by 3, multiplied by 3, multiplied by 2. So this gives us what? 24. Yes, so if you're going to write them out, you have to write out 24 different 3 permutations. So that will take you some time, but I'm sure you will find time to do it. You can try to apply the same formula to the number of 2 permutations because this is what you've been asked to do. What happens if we want the number of 2 permutations from a set? So it will be 4 multiplied by 4 minus 1, which gives us 12. Is that correct? Good. So this gives us the proof of the formula. So we want to pick a set of R elements from a set with n objects. So basically, if you look at it in terms of counting, we have exactly R jobs to do. Because we want to pick R numbers. So this will be the Rth job to do, right? So the first one, we can do it in n ways because we still have all the L elements. But since we can't repeat, the permutation does not allow us to repeat. We only left n minus 1 options for the second. Who is this fellow? Hey. Tafadhali zima microphone. This come Michael and Mudoka. So Michael is refusing to switch off a microphone. I will put him in the waiting room. Okay. Let him stay there until he gets tired. So we can continue. We continue with the proof. So this is the proof. So we have R jobs to do. And in the first job, we can do it in n ways. After that, we can do the next one in n minus 1 ways because we have already used n. 1 has already been used here. So we only have n minus 1 options available for the next job. So we continue in this form, and at the Rth job, we'll have only n minus R plus 1 options remaining. So you simply apply the product rule, and then the total number of ways of filling up these R slots will be the product of all these numbers. R slots. So we have the proof here now. I think it's clear. So I have muted everyone. You will not be able to unmute yourselves. So if you want to speak, you raise your hand. I've tried to be patient. I think it's impossible to get people to behave properly. So here is a proof. We have proved that the number of R permutations of a set with n distinct elements is written in this form. Now this same number can be written as n factorial divided by n minus r factorial. I think you learned factorials in first year, so this should not be a problem converting from this to that. Now, if you are arranging all the n objects, then the number of permutations of a set with n objects will simply be n factorial. So let's check the next one. Here is an example. It says, how many different ways are there to select 4 different players from 10 players on a team to play 4 tennis matches where the matches are ordered? So the key word here is the matches are ordered. And then the other thing we need to note is we are picking 4 from a set of 10. So we are looking for all the 4 permutations from a set with 10 elements. And if you apply the formula, the number of where n is, I think this should have been, n should have been replaced with 10, and r is now 4. So the number of 4 permutations of a set with 10 distinct elements will be given by this 10 multiplied by 9, multiplied by 8, multiplied by 7, which is 5,040. So the matches are ordered, and that means that if they play, for instance, the first 4 players, if they play in that order, that's different from this order. If you have 1, 2, 3. So all these are valid arrangements because order is taken into account. So the next example is, says, suppose that there are 8 runners in a race, and the winner receives a gold medal, the second place runner receives a silver, and the third place runner receives a bronze medal. How many different ways are there to award the medals if all possible outcomes of the race can occur? So there are 8 runners, and any of them can win. I think that's what it says when all possible outcomes are possible. Then you need to pick 3 to award the medals out of the 8. And they can win in different orders. So the order again is important. So since the order is important, the best way to count this is to count the number of R permutation, 3 permutations of a set with 8 elements. And that turns out to be 8 times 7 times 6, according to our formula, which is 336. So I hope that is making sense. So the next thing we look at is another example. So the example says the following. Suppose that a saleswoman has to visit 8 different cities, and she must begin her trip in a specified city. But she can visit the other cities in any order that she wishes. How many different ways can she visit the city? So since there's one that is predetermined, the first city, she has to go to that one first. So it means the order will only change for the remaining 7 cities, right? So the remaining 7 cities, the number of arrangements you can have of 7 objects is 7 factorial, which again is 5,040. So that takes care of the permutations. Now we want to look at combinations. So here we have a definition. We are defining this: an R combination of a set is an unordered selection of R objects from the set. So when we work with combinations, we don't care about order. So we say it's an unordered selection. So this is simply a subset with R elements, a subset of the set with R elements. So let's look at some examples. So if S is this set, this subset consisting of 1, 3, 4 is an example of a 3 combination of S. Now, when it comes to a subset, we don't care about order. We only care about what is in the set. So for instance, you can't, if you reorder the elements in the set, you don't get anything new because we don't care about order when it comes to combination. So if you have a set like this, which contains the same elements, we don't count it as a new one. These and this one are just the same because we don't care about order. We just want the elements that are in the subset. So this and this one are just the same. You can't count them as two different combinations. It's the same combination. Okay. So this is a notation we shall use. The number of R combinations of a set with n elements will be denoted by this. So n will be the number of elements in the set S. So for example, the number of 3 combinations, as we saw earlier here, we counted all of them. The number of 3 combinations from a set with 4 elements is precisely 4. We counted, there's this one, these are all the 4. There's no other subset of with 3 elements that you can obtain. So the other question here is asking you what is the number of 2 combinations of a set with 4 elements. So that requires you to find all subsets. Here we don't care about order. So once we find a subset containing 1, 2, we start looking for other subsets. Keep going. So maybe something like 1, 3. Now, once you find all of them, you will answer your question. You will have found the total number of 2 combinations from a set that has 4 elements. Okay, so here's an example. Actually, it should be a theorem, but this one gives us a formula for computing the number of R combinations from a set with n elements. It's given as n factorial over R factorial multiplied by n minus R factorial. So the proof follows, but it is not complete. A piece of it is missing from the slide. How did this happen? Okay, so we can just get the formula. I will fix it and share the slides when it is fixed. So this is the formula that we need to work with to find the number of R combinations from a set with n elements. So this one is supposed to illustrate how the theorem works. We basically get the total number of 2 combinations from a set with 3. So you list all the different permutations, and we know there are 6, but then they are repeated. So if you want to find the number of combinations, you have to divide by the number of ways any of these permutations can occur. So like this first permutation has 2 elements, it can occur in 2 factorial ways, right? So each of them can occur in 2 factorial ways. So you'll have to divide 6 by 2 factorial to obtain the number of 2 combinations from a set with 3 elements. So you'll end up with 3. So if you look at the theorem, what it has This part is simply, it's P NR, right? And all of this is divided by R factorial. So that's what the example is trying to illustrate. N was 3, R is 2. And we have seen how you obtain PNR over R factorial using an example. So what I have shown is not the proof. The proof is here, but it's not complete. There's a part that is missing down here. But this one gives you an idea of what is happening in the proof after this part. Just observe that this piece alone is the number of R permutations from a set with N elements. Then we have this other piece, R factorial. So let's clear all the drawings. So this is what we have just looked at. Here is a corollary. It says if N and R are non-negative numbers where R is less than or equal to N, then these two quantities are equal. The number of R combinations from a set with N elements is the same as the number of N minus R permutations from a set with N elements. So it is possible to solve this just by direct calculation. We know the formula is this. And if we compute, this is defined as that. So if you compute the number of N minus R permutations from a set with N elements, we still end up with the same formula. So they're equal. So that's one way of proving by direct computation. But we can prove this through a combinatorial, a counting argument. We just count and you'll see what it is. So for instance, if I'm picking from a set of 3 and I want to pick 2, right? So how I pick the 2? The other way I can pick the 2 is by rejecting 1, right? So every time I reject 1, I am picking 2 in some way. Or anytime I pick 2, I must reject 1. So these two quantities must be equal because each of them is doing exactly the same thing. So anytime I pick 2, I must drop 1, and so on. And that's what it says here. If I pick R, I must reject N minus R. And rejection is also another way of picking. So by rejecting N minus R every time, I'm still picking R. And that's why they are equal. So the argument I have given now is what we call the counting argument or a combinatorial argument. So some books will denote the number of R combinations from a set with N elements in that fashion. Then there are others which will also denote it as N, and maybe even on your calculators, it may be denoted like that, NCR. So this means exactly the same thing as, according to the notation we have used, it's the same thing as CNR. So some books may use this and others may use this. We will also use this when convenient. So I think the two notations will be this one, the ones that we use, and this one. So here is an example. It says, how many ways are there to select 5 players from a 10-member tennis team to make a trip to a match at another school? So here we don't care about order. We just want the 5 players, and we are picking them from a team with 10 members. So the answer is quite clear. We simply are looking for the 5 combinations from a set with 10 elements. And if you apply the formula with N as 10 and R as 5, we'd end up with 252 different ways of selecting a team of 5 from a total of 10 players. Okay. So here is an example which we can do. It says, how many ways are there to select a committee to develop a discrete mathematics course at a school if the committee is to consist of 3 faculty members from mathematics? We have 4 faculty members from computer science and 9 faculty members. Something is repeated here. We have mathematics twice. Oh, no. We were fine. We have 3 faculty members from mathematics and 4 faculty members from computer science. And we are told there are a total of 9 faculty members in mathematics and 11 faculty members in computer science. So we must pick 3 out of 9 from mathematics and 4 out of 11 from computer science. So let's see how to solve this. We have 2 jobs to do. One of them is to pick 3. We pick 3 from the maths department. Then we pick, is it 4? Yes, we pick 4 from the computer science department. So in how many ways can we do this job? We are picking 3 from a set with 9 elements. So that can be done in 9 combination 3, or the number of 3 combinations from a set with 9 elements. So this first job can be done in this number of ways. Now the second job here is picking 4 out of a set with 11 elements. So now we have the 2 different ways of doing these jobs. We have N1 and we have N2. So the total number of ways will be N1 times N2. Now N1 will be this, our N2 is this. When we multiply them, we end up with 27,720 different ways to pick a committee of 7 if they are constructed in this manner: 3 from mathematics and 4 from computer science, where we have 9 mathematicians and 11 computer scientists in total. So if you have questions, you can ask. You just raise your hand, then I will enable you to ask. I have muted everyone because you have been misbehaving. So there are no questions? So another identity that we can use for that relates these combinations is this: if you have the number of k combinations from a set with n plus 1 elements, can be written as the sum of the number of k minus 1 combinations from a set with n elements plus the number of k combinations from a set with n elements. So I don't know if we need an illustration for this. So if n, for instance, is, if we have something like, if n is 5, so say n is 5, we'll have 5 plus 1 here. And if k is 2, we'll have, let's say k is 3, we'll have 3 there. So the formula says that this will be the same as C 5 combination 2, that is 1, and then plus the second one is the number of k combinations. So this is just 3 from a set with 5. So this should It's just an illustration of the theorem, but this is not a proof. We're just about to go through the proof. So here, suppose T is a set containing n plus 1 elements. So that n plus 1 is the same here. So we pick one element from T and we create a new set by removing A from that set T. So now this new set S will have n elements, right? So the aim is to find the number of K combinations from a set with n plus 1 elements. So what do you call it? This A can either be this element that we have pulled out of T will either be in a set or not be in the set. So the number we are looking for is this exactly. So we want to split it in, see how we can split it into these two pieces. So if you pick a subset of T, a subset of T with K elements, that subset will either contain A, you have the subset containing A, and then you pick another K minus 1 elements to make it a total of K, right? The other thing, it can also be simply a set of K elements which does not contain A, right? So those are the two ways it can happen. So you pick all the sets that contain A, and for those sets, the only thing you need to do now is to pick K minus 1 elements out of the n remaining ones. And then also consider this set which does not contain A, and then now you can pick subsets with K elements from this set that does not contain A. So that gives you all the possible subsets with K elements. And that's how you get the 2. I think it continues on the next page. If there's anything that's not making sense, you raise your hand up, you will be able to speak. So this is what I was just saying. We have two ways of finding a set with K elements. Either you pick a set with K elements that contains A, and if A is fixed, then it means all you have to do is select K minus 1 elements from the set S. So I select K minus 1 elements from this set S, then I can put them together with A to get a set with K elements. That's one way. Then I can also consider all the subsets which do not contain A, but have K elements. And that means I just pick K elements from this set S, because this set S does not contain A. We have removed A from this set. If I pick K elements from this set, I get all the subsets with K elements which do not contain A. Now, if I add up those two numbers, I get my total number of subsets that have K elements from a set with n plus 1 elements. So it's also possible to prove this using some algebraic manipulation. So you just apply the formula for computing this and also the formula for computing this. Then you simplify and show that it is equal to the left-hand side. Are we together? So I hope you have had enough time to digest this one. So this formula also works. This one is called the Pascal's identity. You have seen this in the Pascal's triangle, because what happens is Pascal's triangle works like this. You have 1 and 1 here, then 1 2, 1, and 1, 3, 3, 1, and so on. So Pascal's triangle works like this. If you want to get 3, you'll have to add 1 and 2. So what is 3? 3 is obtained as what? 3 combination 1. But this is not a good example. We need a larger number. So let's keep going on. We have 1, 4, then we have 4, 6, sorry, then 4 and 1, like that. So if you want to get 4, we will have 3 plus 1. So it's the addition that's going on this end. So here, if you want 4 again, if you want 6, it is 3 plus 3, right? So this one, I think, should be something like 4 combination 2. So 4 combination 2 is the same as 3 combination, is it k minus 1? 1 plus 3 combination. But both of these are 3. So this is 3, that is 3. Those are these 2 3s that we have up here. And we have a 6 here. Let me rewrite this properly. So we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, and 4. So this is just a Pascal's triangle. You can get this. So I was giving an example here that 6 is the same as 3 part 3. But 6 is supposed to be 4. The coefficient there will be 4 combination 2. And if you apply our formula, then this should be equal to 3 combination 1 plus again 3 combination 2. So it works in the Pascal's triangle throughout. So it keeps going on. You can extend this further. You'll have 5 here, you'll have 10, and so on. So all these can be expressed in this manner. 10 and 10 is given as 6 plus 4, and so on. 5 is given as 1 plus 4, and it keeps growing. So then there's also another identity here. It says the following, that if you add up these values, then it should be the same as 2 raised to n. So let's write out a small example. So for instance, if n is equal to 3, then if you expand this summation, what you will have, because k will run from 0 up to n, right? So if n is equal to 3, then you will have, the first thing will be 3 combination 0. Then plus the next one will be 3 combination 1, and so on. If you keep expanding this, you will get 3 combination 2. And last but not least, 3 combination, should be a C here. Should get C combination 3, 3, 3 here. So the claim is that this now should be equal to 2 cubed, which is equal to 8. So that's an example of what this formula would look like if n is 3. Then you can expand it like that and get all the possible cases. So let's check, will this actually 3 combination 0 should be 1, right? There's only one way of picking nothing. And then, but this one follows from the fact that we define 0 factorial to be equal to 1. If you put this back in the formula, 0 factorial is defined as 1, so that's why you will obtain 1 here. Then this is 1 also. And this one is what? 3. And this is 3. So does this get to 8? 1 plus 3 plus 3 plus 1. That gives us 8. But this should work for any general value of n. So we want to see how do we prove that it is true for all other values of n. So let's see how we go about that. So we'll do this. We'll count in 2 ways. So if a set has n elements, then it has a total of 2 raised to n subsets. So that's one way of counting the subsets. But we can use these combinations also to count the subsets. So I can count the number of subsets with no elements will be n combination 0. Now the number of subsets with only one element will be 1 combination n. So this continues like that. The number of subsets with the 2 elements will be n combination 2. So this goes on like this until we get to the final one will be the number of subsets with say n minus 1 elements. And then the final one will be the number of subsets. The whole set, the number of subsets with n elements is just the whole set, right? So this counts all the subsets. So if you add all these things, you'll have added up all the subsets of a set with n elements. But we know that to be equal to 2 raised to n. So that's why this quantity here is equal to 2 raised to n. So that's the final bit. We have proved that what this quantity here does is simply count the number of subsets of a set with n elements. But from our previous work, we know that the number of subsets with n elements will simply be 2 raised to n. So these two must be equal. Okay. So that is the binomial theorem. What we can do also is we can take a 5-minute break and continue after 5 minutes. Maybe I can see if it's possible to allow you to speak now so that we have a discussion on this. So now you can, if you wish to speak, you can speak. You can put on your mic and speak. So take a 5-minute break. Yes.
Can you please return to where to our last part where it says, where it gives us the function of this summation of n over k? Yeah, that part. Leave that. I want to write something small there.
Okay.
The next page, not this one.
But you have these notes, eh?
Yeah, but I want just to write that. Yes, there. Thank you.
Okay. So we resume in about 5 minutes.
Yeah, okay.
So Philip is asking if you can be asked to prove these theorems in exams. Yes, you can. You are no longer in high school, man. You are not. You need to change your mindset completely. Everything we're learning in class is examinable. So you can't hear me because I'm not speaking. Eh? We are taking a break. So now you can continue. So now we talk about the binomial theorem. This when you expand the binomial expression, you need to find the coefficients of the terms, and this binomial theorem allows us to find them. So that's what we are going to do in this part. So we start with a small example. We look at this binomial x plus y raised to 3. One way to find it is simply to expand it in this form and multiply it out, and you will still get the answer. But the other thing you can do is to observe that there are only 3 types of terms that will occur. The terms where x is raised to 3, but then in that case, y will not be in that term, then x squared y, xy squared, and then y cubed. So to obtain the term x cubed, it means you need to pick one x from each of these, right? From each of these factors, you need to pick an x. Then when multiplied, you will get x cubed. So that can be done in only one way. So when you multiply it out, the coefficient of x cubed will just be 1. Now, if you are going to get a term in x squared y, it means you need to pick out of these two terms, it means you pick x from two of these terms. Out of these three terms, you pick two x's and one y, right? So you can pick two x's in two combination 3 ways, because it means you pick from any two factors, and that is 3. Since there are 3 factors, if you want to get two x's, we simply pick two x's from two of these factors. Then to get the y is picked from the third one. And that can be done in 3 ways. So one of the ways is to pick an x from here and x from here to get x squared. Then that will be multiplied by the y here. Another way is to pick an x from here and x from here to get x squared, and that will be multiplied by the y here. And then the last one is to pick an x from here and another x from here, and that product of x squared will be multiplied by this y to get x squared y. So you do that in 3 combination 2 ways, which is equal to 3. So the coefficient of x squared y will just be 3. So the same idea can be used for xy squared. You pick one x and reject the and use that x to multiply with the other 2 y's to get y squared. So if you are counting how many ways to pick x, that will be 3 combination 1, which is again 3 ways. So the only way to obtain a y cubed term is to pick y once from each of the 3 terms. And again, that can only be done in one way. And that means the coefficient of y cubed will be 1. So now that you have all the coefficients, you can write out the expansion of this binomial. X plus y raised to 3 will be equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. So this will serve as an example as we continue to state the binomial theorem. So the theorem says the following: let x and y be variables and let n be a positive integer. Then the following will happen: x plus y raised to n will be equal to this expansion. You will sum from j is equal to 0, n combination j multiplied by x n minus j multiplied by yj. If you write it in full, this is what it will look like. And these ones are what we call the binomial coefficients, all this. So the only thing that has changed there is instead of the previous, in the example, n was 3. Now we have a general value for n. It can be anything else. And you can plug it into this formula and get the expansion like that. So this is what we call the binomial formula. And therefore you can be able to get using this, you can always get the coefficient of any of the terms for a binomial expansion, or the power of a binomial. So here's an example which is asking what is the expansion of x plus y raised to 4. And if you apply the formula, this is what we get. You simply plug in everything and compute. You can compute all this with your calculator, and you'll find that these are the coefficients. Although these are, you can easily pick them from the Pascal's triangle. It will be quite easy. So here there would be no challenge, but it's just to illustrate the theorem. As usual, if you have any questions, you just put on your microphone and speak. I have not muted people again.
Please pardon. from the first sum, the one was x plus y to power 3.
What do you want me to do? You want me to repeat?
Yes, at least, pardon, please, from the beginning of it. After you started.
Now I hope this time you will pay attention.
Yes, please.
Yes, catch on you one. Okay. So we want to expand x plus y cubed. So one way you can do it is simply to expand this whole thing, multiply it out, and you will get your answer, right? The other way is to make the following observation. These are the only terms that will occur in that expansion. So to find the coefficients of each of these terms, simply count the number of ways that they occur, and that will give you the coefficients, right? So we can count the number of ways to get x cubed, and that will be the coefficient of x cubed. The number of ways to get x squared y, and that will be the coefficient of x squared y, and so on. The number of ways to get xy squared, and so on up to y cubed. And those will give us the coefficient. So let's move one by one. So the first term is x cubed that we'll look at. How do we obtain x cubed? When you're multiplying this out to obtain x cubed, you need to have an x from each of the factors. Each of these three factors will have to contribute an x. So you can do that in only one way, right? Once you get all the x's, one from each, there's no other way to get x cubed. So it means that can only be done in one way. And therefore the coefficient of x cubed in the expansion of x plus y cubed will just be 1. So we have 1. So the next term we have is x squared y. Now, if I want to get x squared y, how do I obtain this? There are a number of ways I can do this. I can pick this x and this x to get my x squared, and then I will multiply that by y to get x squared y. That gives me 1, right? So it means I have to pick 2 factors to give me my, out of the 3, to give me my x squared. And then to pick 2 factors, the number of ways I can do that is 3 combination 2. I have 3 factors. For me to get an x squared, I need to pick 2. I can do that in 3 combination 2 ways, which is equal to 3. So that tells me that the number of ways, the coefficient of x squared y will simply be 3. Now, if I need to get xy squared, I just, because we are counting the number of ways of picking x, I just need to pick 1 x, and then the y squared will come from the other 2 terms, right? So I can pick 1 x out of the 3 in 3 combination 1 ways. So I can pick 1 x because I need only 1 x. The y squared will come from the other 2 factors. But once I pick 1 x, that's enough. Another x that I pick will give me another y squared. Another x that I pick will another y squared. Eric, hey, you guys cannot be helped. I think I will mute everyone again. So we continue again. We've seen that the number of ways this xy squared term can occur is 3. So the coefficient of xy squared will be 3. x cubed y, xy squared, and y cubed. And we've been able to establish the coefficients as 1, 3, 3, and 1. And we've been able to obtain these coefficients using this binomial, number of combinations, counting combinations, right? So I hope that is clear now. Was it Lopuo? What was the name? I can't remember the name. The person who asked, if you want to speak now, you will have to raise your hand so that I can I can open your mic. So based on that, we can generalize it to this. If you want to find the expansion of x plus y raised to n, then the terms that you will need will be terms such as x raised to n. Then the next term you will need is x raised to n minus 1 multiplied by y. So this keeps going on, x raised to n minus 2. But now you multiply by y squared and so on. This goes on until you reach the last term, which is y raised to n. So here you'll have n factors. If you want x raised to n, it means you pick one x from each of the n factors. That can be done in okay, maybe there's this thing. This can be done in so there are two ways to do this. Either you pick x once or you don't pick any y. Yeah? It can be done in only one way, yeah? Because you pick x from each of the factors once only. There's only one way to pick x from each of the factors to get x raised to n. That is just one. But we can write that as n combination 0, because n combination 0 is 1. So now the next one here, you have to pick n minus 1 x's, right? So it means you have to pick n minus 1 x's. So this notation also means n combination n minus 1. But remember, we had seen this identity earlier, that this is the same as n combination n minus n minus 1, right? So this will still be the same as n1. That's how you can justify this formula. So you can still write this as n1, and using the same argument, you can write all the rest as they are. The formula we're using here was that we saw earlier that if you have n combination r, this should be the same as n combination n minus r. So that works. So here we are picking n minus 1 x's, but it's the same as picking 1y. So it doesn't matter which one you put, whether you put this one or that one, it is the same value. So you go on with the same fashion until you have all the coefficients, and that gives you the binomial formula. So I'll put on the mic briefly to find out if your question was asked, was answered. So are there still any questions on this? The gentleman who had a question, are you happy with the answer now? You won't say. Okay. So we had looked at this, applying the same formula for x plus y raised to 4. You expand it and this is what you'll get. But like I said, this one is easily obtained from the Pascal's triangle. It's not a big challenge, but it helps us to illustrate the theorem with a small example. Then this turns out to be a little more interesting. So if you have x plus y raised to 25, how do you find the coefficient of x raised to 12 multiplied by y raised to 13? So the coefficient will simply be this, if you follow the binomial formula. It's also the same as C25. What you will notice, again, this is the same as So there are two ways you can do this. I'll explain that in a minute. So C25, 12 will also give you the same answer. Because why is that the case? Because if you pick, there are two ways you can do. You can choose either to pick the x's or pick the y's. So if you are picking the x's, you need to pick 12 of them from 25 factors. But if you pick 12 x's, then you must reject 13 y's. So these two are counting exactly the same thing. Anytime you pick an x, you'll be rejecting a y. So if you count the number of ways rejecting x, it's the same. If you count the number of ways of rejecting 13 y's, it's the same as the number of ways of picking 12 x's. So these two can work. But for the purposes of standardization, we stick to this formula. But now you know why it works, and there should be no confusion. So we just follow this formula and apply it to this question. And our answer will be 5,200,300. That's the coefficient of x raised to 12 multiplied by y raised to 13 in the expansion of x plus y raised to 25. Okay. So I hope that is making sense.
Yes.
So here is another example to find the coefficient of x raised to 12 and y raised to 13 in the expansion of 2x minus 3y raised to 25. So here what we do is we write it in a form that's easier to work with. So we write it in this form. So treat 2x as your first term in the binomial and negative 3y as the second term. And if you write out the binomial expansion, this is what it will be. So your interest is to find 12 x raised to 12 multiplied by y raised to 13. So that will happen when this quantity is 12 and when this one is 13. So if j is 13, you'll have 25 raised to 13, but we have a 2 here, right? Yeah, x is raised to 12, right? So x is 2 raised to 12, because this will be 25 minus 13, that will be 12, and then multiplied by the other coefficient will be minus 3 raised to 13, because j is 13. So this gives you the complete coefficient of x raised to 12 multiplied by y raised to 13. Now this number is too big. You can't, even your calculator cannot compute it, I think, if you work this out. So you just leave it in that form. So this is not negative. This should be plus. There is no negative here. I think this is a typo. The answer is just this number. Okay. So there's this identity we saw earlier, that this quantity is equal to 2 raised to n. We already proved it earlier by counting the number of subsets, but we can also use the binomial theorem to prove it. So we know that 2 is the same as 1 plus 1, so we can replace 2 with 1 plus 1, and we raise it to n. And we treat this one as our x, and this second one as our y. Then we put it in the binomial expansion. And this will simply be equal to Cnj. So for instance, when this one is just powers of 1, eventually this will be equal to 1 raised to n, because 1 n minus j multiplied by 1 raised to j is the same as 1 raised to n. and 1 raised to n will just be 1. So this thing will always be 1. That's why we're ignoring it in the next expression. So we proved this earlier, but we are proving it again using the binomial expansion. So here is another one that makes use of a binomial expansion. So if you have minus 1 raised to k multiplied by c raised to n, cnk, then you sum all this over k, where k runs from 0 up to n, they claim that the answer should be 0. So the trick to solve this is to notice that 0 can be written as -1 plus 1, and 0 raised to n is just 0. So you can raise this whole quantity to n and apply the binomial expansion. And this is what you will have. And this will simplify this term in this terms that we're adding. They can be simplified to this form if you observe them carefully. Because -1 raised to n minus k will give us there's something not right here. This should be, I'm using j, this should be k. This is k here, right? So this one should be k. K is equal to 0. And this should be even here, it's the indexing is k. I don't know why I have j. So this is k, this should be k. Will be summing over k. So this one simplifies to this, which is exactly what we have in the theorem. But you make use of the binomial expansion and the fact that 1 plus 1 is equal to 0, and that 0 raised to n for a positive integer n will still be 0. There's someone again switching on the microphone. Exactly as expected. So I think we'll stop here for today. We'll continue from there next time on the next topic. The next topic will be combinations with repetition. Unless there are questions? Do you have any questions? So asanteni sana for showing up. We'll meet on Friday at 8. If you have any questions, you should ask.